Hello, marvelous Calculus AB students. Day 72 brings us to the conclusion of the second part of this unit, where we began with antiderivatives. Remember those indefinite integrals where like, what's the antiderivative of sine of x dx? And then you're like, oh, that's negative cosine of x plus c. Remember all that? Yeah. It's not in the past forever. It will be coming back to rear its friendly head shortly. That was the first part. This second part was all about definite integrals, right? We had something from a to b of f of x dx, and we discussed how that measured the area, the signed area between a curve and the x-axis. And today is actually going to conclude that lesson, or that little subsection, where we originally used geometric formulas, and you do need to know how to do that. You need to know how to find the area underneath a circle or areas that make triangles. But then we got to a bunch of areas where we couldn't use nice geometric formulas, and so instead we started approximating. We approximated with left, right, and midpoint rectangles. We also used trapezoidal approximations, and we said that those are doing a pretty good job. And the last couple of days we've discussed how we could maybe more efficiently write those, and that I think brings us to the opener for today. Once we get through the opener, the rest of today is how can we take our approximations and not only make them better, but how do we make them the best? Or that is to say, how can we turn our approximation into the exact area under the curve? And the answer for today is a little bit of a letdown, but you'll only be temporarily disappointed because next class, day 73, is our big reveal. Next class, we learn the fundamental theorem of calculus. Yes, one unifying theory across calculus, and it is the big one. So I always call it the big reveal, and we're going to get there next class. We still need to do this class. So let's go ahead and attack that opener. Give you a couple minutes for it, and I think you can read through the first one on part A. You're going to have to write two Riemann sums here, and so I'm going to leave a little space up at the top for some work, and then I'm going to do one Riemann sum down here, and then it's going to be equal to another Riemann sum over here. And it's okay if you're not quite sure what to fill in yet. You can read this, and we'll do it together in a bit. And then part B is a little bit extra. It's saying, okay, you found some Riemann sums, and if you have time, you can use your calculator to figure out the answer. We'll use Desmos to look at that. And then I'm going to say, well, here's the exact area. And you're going to have to decide if your approximation is over or under, and then how you could improve that approximation. So again, take a few minutes, try part A. If you get stuck on it, you can look at what we finished day 71 with, and then also please attempt part B. Ready, set, go. All right, well, how are we going to do this? We know we're going on an interval from 1 all the way up to 5. They want us to use 16 subintervals, and so I believe that gives us delta x 5 minus 1 over 16. That is 1/4, 4 over 16, right? So each time we're going to bump up 1/4. So our first x value on the x-axis is 1. We add 1/4, which is 1 and 1/4, or if you'd like, 5/4. Add another fourth, that's 6/4, 7/4, and we get the idea, I think. And we go on up forever. So this 1 I'm going to treat as 4/4. We, of course, also know we need to add those together, and we need to add up 16 of them. It is a left Riemann sum, which means we'll exclude the 5. We'll stop right before the 5. But in fact, we don't even need to find that number, though. We'll see what it is shortly. I think we probably have enough information to skip to our Riemann sum. So we start with the idea of base times height, and although we've always done base times height, for today we're actually going to switch the order and we're going to do height times base. The reasoning for that will become clear next class, and actually no, this class as well I think is fine, but it is more commonly written to do height times base, so we're going to do the base at the end. Okay, our base is delta x though. Right? Each base is a consistent 1/4, so I'm going to be multiplying by 1/4. There's my base. But what about the height? Well, these are x values. X values don't tell us the height. We need to convert those into y values, and to do that, we need to substitute them into our function x cubed. Okay. Now to do that, we need to determine the pattern that's going on here. Luckily, there's a consistent 4 in the denominator. And the numerator is going up by 1 every time, so I know my slope is 1n, or just n if you will. And then we see if we did it right. If we substitute 1 in here, do we get the first term of 4 over 4? No, if you say no, if you substitute in 1, you get 1/4. We want it to be 4/4, so we need to add on an extra 3 to bump everything up. Now we get 4/4 from n equals 1, n equals 2, we get 5/4, and so on and so, no pun intended, forth. Where do we stop? Well, if you start at 1, it's very easy to determine where you stop. You wanted 16 subintervals, so 16. And there we go. This would give us our Riemann approximation for the area under the curve. And then it did mention that we could use f of x equals x cubed to rewrite our height. This is something we'll do often today. So we're still going to go from 1 to 16. It's still going to be times 1/4. But instead of f of n plus 3 over 4, let's be more specific. And let's say this is n plus 3 over 4. Whatever that x value is, if you substitute into f up here, you need to cube that. Alrighty. Mr. Grant is giving you the exact area below. So I'm telling you right now the exact area from 1 to 5 beneath x cubed is 156. Right? That is not an approximation. There is a way to determine the exact area. And so I guess the first question is our approximation from A an over or under approximation? Well, let's go ahead and look at the graph quickly. You guys should know what the graph of x cubed looks like, but if you don't, I do have this prepared. Hopefully, though, you realize that this is an increasing function. It goes to infinity, right? X cubed increases all the way up, and we did a left approximation. So maybe envision this is our subinterval right here. We could draw a rectangle, or we could look at this subinterval, and we start on the left side. We draw up, over, and down. And this rectangle of these 2 blocks is clearly less than the 2 blocks plus this almost triangular shape up here. So I'm pretty confident that my left Riemann should be an under approximation. If I were to do a right Riemann, same subinterval, I'd go up, over, and down, and I would fill in this extra piece up here, so that would be an over. Now let's actually see what we found for this Riemann sum approximation. I'll keep that f of notation so it doesn't get too confusing here, and we'll use Desmos to do it. You can do this on your graphing calculator as well. With Desmos, we just type in sum, n equals 1 to 16. The height first was f of, and it's n plus 3 over 4, I think. But then we needed to multiply by the base, and the base was 1/4. And so we set our left Riemann sum approximation 140.875. Not bad. The exact answer is 156, right? So we're a little bit low there, but we should be low because it's an under approximation. If you made this a right Riemann sum, it should be an over approximation. How do we make it a right Riemann sum? It's easy. Just start one more. Boop. And now we're an over approximation, right? Because now we start at 5/4 instead of 4/4, and 171 is an over. We did learn before that sadly we can't average the over and under every time, most times I would argue, and get the exact, because this doesn't increase, the graph doesn't increase evenly. So let's go back to that left, and then we're going to answer our last question of, well, how do we make it more accurate, right? So if we had just looked from 1, which is right here, from 1 to 4, and we'd done a left Riemann sum like a single rectangle, the single rectangle would have been very inaccurate. That would have been a 3 by 1. It would have said an area of 3, not even close. But then if we'd done 2 subintervals, we would have been more accurate. We did 16, and that's actually much more accurate, but can we go more? Of course we can. We can always do more subintervals. So when the question is, how do you improve your approximation? How do you improve your approximation? The answer is create more subintervals. Instead of splitting from 1 to 5 into 16 subintervals, let's see if we can alter this and do 32 subintervals. I know I'm going to have to go from 1 to 32. Is that as easy as it is? Oh no, that's way too large. And this is still an under approximation if it's a left. Where would we start? Or maybe how big is each subinterval? Well, if it's 32, we have a 5 minus 1. It's still 4, but it's 4 over 32 now. And I think that's going to give us a 1/8. So our base is 1/8. And our x values are going to go up by 1/8. we are going to start at 8 over 8 at f of 1. So 1 plus what brings us to 8 over 8? 1 plus 7. And notice now we have a slightly better approximation, 148, as opposed to, just reminding you, that we originally had this guy. Let's see how quickly I can get back there, as opposed to this one. There we go. So this was close. This is closer. How do we get as close as possible? Well, we do the most subintervals as possible. And that is going to be our theme for today. How do we do the most subintervals possible? And is there a way to do a number of subintervals that gives us the exact area under the curve? So let's get into our lesson. There's going to be a bit of notation on this first page, and then we'll really look at one example, and then we're actually done with notes for today, and most of it is going to be you guys practicing. So let's begin. We're going to first look at how we can notate moving from one x-coordinate to the next, so moving along the x-axis when you're approximating the area. Now, we've actually done this before, but we're going to formalize this here. So if you're on an interval from A to B, and you can, and I'm reading up here, but you can kind of glance down here to use this as some help, we're going to assume that we begin x equals A. For the ease of today, we'll assume this is a left Riemann sum approximation. If it was a right Riemann sum approximation, you begin at the next x-coordinate, but it's easier to start at the initial one. We do need to remember that the length of each subinterval is noted as delta x. So that would mean then that the next x-coordinate after A is given by A plus delta x, right? If this is A right here, then this is A, but moved forward delta x units, right? Delta x in our opener was 1/4, so if we started at 1, we moved up 1/4. All right. If you wanted to go further than that, if you wanted to do this next one over here, we again start back at A. That's our fixed starting point. We add delta x to get to this guy, and then we add one more delta x to bring us to the next one. Of course, writing A plus delta x is a little bit excessive because we can simplify that down to A plus 2 of those delta x's. And so we actually notate a general x-coordinate in this as x sub k, where the sub k is just representing an x-coordinate, right, is given by A plus k of those delta x's. Adding k delta x's just adds k number of subinterval widths, so let's look at a couple examples down below. If you wanted x sub k, where k equals 1, then that would mean you are going to start at A and add 1 of those delta x's, and that will move us to x sub 1. If you wanted to move to x sub 4, that means k is 4, so you add 4 of those delta x's to A, and that gets you over to x sub 4. If you think about it with f in front of it, then if we said f of A plus 5 times delta x, then that's going to move us to the x sub 5 coordinate, this guy over here, and then f of that actually is finding this height. It's actually finding the height of our sixth rectangle over here, right? 1, 2, 3, 4, 5, 6. It's finding the height of our sixth rectangle. Now, delta x is some sort of arbitrary distance. In the past, we found an actual concrete number like 1/4 on the opener. It can be as large as you would like, though it's going to be less accurate, or it can be as small as you like, and the smaller it gets, the more accurate it is. It still represents the base of our rectangle, and it tells you how you move between x values. So it's not too much of a jump in logic then to show this formula below that can represent the sum of the area over on the right. Now, there's a couple things that are a little different here, but I still think we can probably annotate this formula to identify the base and height, and the weird part, why it's starting at 0. So let's start with the base. We know delta x every time has been our base. Nothing has changed. Okay? A plus k delta x, this piece inside is just moving us to different x coordinates. And then once we've moved to a specific x coordinate, f of that x coordinate finds the height. Now, why are we starting at a k of 0? It's just all on how you write the formula. So at k of 0, we substitute 0 in here, and it says start at A and move 0 delta x's. And for a left Riemann sum, isn't that what we want? We want to start at A, don't move at all, and then do f of A to find the height of our first rectangle. And then we have the base over here, And look, it makes an L, left Riemann sum makes an L, and now you have the area of the first one. And then when you ratchet this up and you say k equals 1, now it says start at A, move one of those delta x's, so that moves over here to x sub 1, f of that finds the height, and then we multiply by delta x, left makes an L, and you now have the base of your, or now you have the area of the next one. How come we're stopping at 6? Because there are 7 rectangles. Well, that's just because we started at 0. If we went from 1 to 6, that'd only be 6 rectangles, but 0 to 6, count on your fingers, right? 0, 1, 2, 3, 4, 5, 6. There are 7 numbers from 0 to 6. Always tough to think about. Now, the cool part for today. We discussed how the more subintervals you give, the more accurate you're going to be, which should suggest then that if we did the maximum number of subintervals possible, that we should probably be infinitely close to the answer. So how many subintervals are possible if we're thinking of this number up here as approximately the subintervals plus minus 1 depending on where we're starting down here? Well, wouldn't that mean that we need this number up top to be infinitely large? Now we can't just replace 6 with infinity because eventually we plug 6 into an equation, and we can't substitute infinity in because infinity is not a number. Infinity is just a concept, right? It means really, really big. So how do we get around that? Well, we can actually define exactly, no more approximately signs here. We can exactly define a definite integral to find the exact area under the curve like so. And we've seen a lot of this before too. So let's re-annotate. We know that delta x is still the base of a rectangle. You can put a little times in here if you'd like. We know that f of all this is still the height of a rectangle, height times base. Base times height if you want to think about it. We're still starting at k equals, I started at k equals 1 here. You could also start at 0. This would probably make this a right Riemann sum because you're starting 1 delta x to the right of A, but it doesn't matter one way or another. And then we have n up at top. Instead of a number, we have n, but look what's out front. The limit is n approaches infinity. They're saying take n, where n could be the number of subintervals, and run the number of subintervals to be infinitely much. Now, infinitely large is kind of weird because if you have an infinite number of subintervals, they're actually infinitely small subintervals. Yeah, kind of confusing, huh? Your book defines this a little bit differently, which is fine. It still works. I just normally see this in the AP definition as opposed to how your book does it, but this is all over the place too. It's very common. So let's see if we can parse through this formula, and then we'll do one example and call it good. So the exact area under a curve is given by the limit as delta x approaches 0 from k equals 1 to n, f of x sub k times delta x sub k. Well, what are they doing here? If they bring delta x to 0, that's the base. So they're saying that we want to find base times heights, where the base over here is infinitely small. But if your base is infinitely small, and we need to get from, let's say, 1 to 5 again, but each base is infinitely small, how many bases are there going to be from 1 to 5 if each base is approximately 0? Well, there's going to be an infinite number of bases. So it's just a different way to look at it. Instead of saying make an infinite number of subintervals, they're saying make the base infinitely small. Now, although it would be really, really exciting to use either of these formulas to actually find the exact area under a curve, it's unfortunately beyond our current knowledge, or at least most of our current knowledge is, because we don't spend enough time with infinite series in either this course or in pre-calculus. If you had tons of time in pre-calculus, they would take you through how to find sums of series using different formulas, and it's very cool, very exciting, but we haven't done that, at least in our school. So maybe other schools have, and if you have, that's great. I'll show you where you can look in your book if you want to learn how to do it, but it's actually not expected on the AP exam that you ever use this to find the area under the curve. However, it is expected on the AP exam that you can convert a definite integral into its summation definition, which is what this is over here, or go the other way. If they give you a summation, tell us what the integral is for that. So what we're going to focus on today is how to convert between the two, but not actually how to find the area. And the reason that they don't ask you to find the area doing it this way is because there's a shortcut. And that's our big reveal tomorrow. Instead of doing all this crazy math we're about to see, what is the shortcut? Well, stay tuned. Now, of course, some of you might say, well, if there's a shortcut, why are we doing this? The AP exam likes to test, especially in the last couple of years. They'll ask a multiple choice question of, what is the summation definition of an integral, and you have to match it. So they do want to make sure you know the concepts before you just get the shortcut. And they're pretty good about asking those. So let's take a look at our example. Find the exact value of the definite integral below using a right Riemann sum and letting n approach infinity. So the reason we're doing a right Riemann sum now is because we're going to start at k equals 1 in our summation, which means we're going to add 1 delta x right away. So instead of starting at a, we're going to do a plus 1 delta x. We're going to start 1 x coordinate ahead of a. If it was a left Riemann sum, the process is the same. You just start at k equals 0. Just giving you a heads up. But either way, they're not going to try and trick you like that and give 1 at 0, 1 at 1. They're just going to give you all the same thing. So you really don't need to focus as much on this. It's all about this part, the height and the base. Okay, our goal is to find the exact area below the graph of x cubed plus 1 from 2 to 6. And we are actually going to sketch the graph here. You're going to want to leave a decent amount of room underneath the x-axis, though, because we're going to be annotating. So make sure you're ready for that. X cubed plus 1 starts 1 above the x-axis, and then it just kind of looks like a parabola from here, honestly. I mean, realistically, it looks like this, but we're going to stretch this graph out so we have a lot more space. We are going from 2 to 6. This does not have to be perfect. And then we want to find the exact area under the curve. How do we do that? Well, first thing we're going to do is we're going to set up our limit definition, and then we're going to start to fill things in. Now, do you have to memorize the limit definition? I would say probably yes. If you can read through their definitions and understand what's being asked, then probably no, but I found it's easier in the past if students just memorize this one. So what does that look like? Well, we're going to take the limit as n approaches infinity, the summation of k equals 1 to n. Do you need to memorize that part? No, that'll be on every single one of the summations. It's not going to be a free response, so that part's not memorized. And then we're going to build up on this, a height times a base. Okay, think you can memorize that? Because if you can memorize that, you can probably get to where you need to go. Base times height, that's how you find an area, and then we sum up the area, that's our Riemann sum. Okay, let's make this look a little better. The limit is n approaches infinity, k equals 1 to n. Leave the height blank for now, but we know that the base is delta x. Well, that suggests then that we should probably find delta x, huh? So let's maybe do this over here. Delta x, length of the interval from 2 to 6, divided by the number of subintervals. What's the number of subintervals? Well, every time we've started at 1, the number of subintervals has been the number at the top. And instead of a number, we have a letter, but it's the same idea. It's going to be n. So we're going to be doing the length of the interval divided by an infinite number of subintervals. Okay, I should have left a little bit more space here, but that's okay. And so we're actually going to do one more, and then we're going to backtrack and fill in the rest. So we have the sum from k equals 1 to n, and we now know that delta x is 4 over n. All right, we're looking good so far. If we're looking at this piece right here, we're going to need to do f of something. And f of what? Well, it's going to be f of each of the x values. So where do we start? We always start on the left side of the subinterval, so we always start at a if we're going from a to b. And then we're going to add some number of delta x's. Start at a, add delta x to move yourself along until you get to 6. We can fill in those pieces, though. This isn't too bad, I don't think. We know a, the start of the subinterval, is 2. K is just an unknown number, right? K is going to increase every time. And then delta x over here, we just found that. That's 4 over n. Very exciting. Okay. Last but not least, we are going to, see, I told you it's pretty quick. We're just going to take this f of whatever, and we're actually going to substitute this in to our equation, x cubed plus 1. So, zooming in, we have this 4 over n at the end, and then we have x cubed plus 1. What am I substituting in? 2 plus, and if this is k over 1, let's write that together, 4k over n. And that's it. That's all you're required to do. Now I'm going to re-summarize this so that we have a nice handy-dandy way to take notes, but I think it helps to look up here and understand that a plus k delta x. What that really means is after 2, my next subinterval here is going to be 2 plus 4 over n, right? If delta x was like 1/2, this would be 2 plus a half, we'd be at 2.5. My next one over here would be start at 2 again, add one of those 4 over n's, but that just brings me right here. Then we need to add another 4 over n to get to the next one. And a way to phrase that is you added 2 of those 4 over n's. If you want another one, 2 plus 4 over n brings us to the next x coordinate, plus another one, next x coordinate, but we need to go one further, next x coordinate, which is 2 plus 3 of those 4 over n's. That's all our k is saying here. It's just how many x coordinates we're moving along. Okay, summary. Part 1, you calculate the width of each subinterval. This is just a fancy way to say delta x, so we found the total length of the interval. We said it was 6 minus 2 for a total length of 4. We divided by an infinite number of subintervals, n in this case, because n is going to infinity. We identify where each of the subintervals start. This is like finding our x values for our right Riemann sum. It's that a plus k delta x. Okay. We already know, and we're just going to fill in each of these pieces, right? We know that a is 2, and delta x is 4 over n, so we just get our a of 2 and our delta x of 4 over n. Now, I went ahead and rewrote this, and if you wanted, you could go even further. We could, give common denominators and put everything together, but generally, I would say probably never do you have to go that far. So I would say probably stopping here is just fine. Part 3 is actually putting everything together in our height times our base, right? We have our height right here, and we have our base right here. Now, I took this guy and put it in here, but I'd suggest that you take this one like we did earlier. And then, last but not least, we substituted everything into x cubed plus 1. Now, if your pre-calculus skills are really good, then you can actually mathematically go further and determine the answer to this. As a spoiler, and I tried this on the other page, it ends up being 324. There's a typo on my original one. So this equals 324. Okay. You don't need to be able to go from here to here for this class. We're going to find a shortcut. If you do want to learn more about how to do that, you can check out 2 different pages in your textbook, one that shows you how to find sums of these infinite series, and then one that shows you how to put it all together. Okay? But again, all you need to do for this exam is to know that this guy is the same as this one. And again, this part is even a little bit too intense for what we have to do. So finishing today, we do still have some unanswered questions. Right? And our 2 big unanswered questions, number 1 are, how do we actually find the exact area so that we don't have to have the knowledge to turn this into 324? And then the second question is, how do indefinite integrals relate to definite integrals? They seem very unrelated. Indefinite integrals give us an equation. They undo a derivative, and derivatives have to do a slope. And definite integrals are all about calculating area. So how do derivatives and area relate with each other? And we are going to answer those next class with our big reveal. The last part of your class today, though, is just to practice the summation definition of definite integrals. So what does that mean? Well, they're going to give you an integral, and your goal is to follow the same steps that we did up here, 1, 2, and 3, right? And you're just going to be figuring out which one this matches. And once you figure out, and there's enough space here for you to show work, once you figure out which one it matches, you can just say that this one goes to, let's say it matches 2 or something like that, right? There are 10 questions here, though, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you're going to have to work each integral here. I will tell you that the trickiest ones are the ones that have multiple instances of x. So if you want a really a pretty straightforward one to start with, you actually might want to start with j. That's the easiest function. I will say that I and h are both going to be definitely a little bit harder, and that g and f are probably going to be the trickiest just because they have multiple x's. There's some minus ones there. Life's going to get a little wild. If you do ever get stuck, you are always welcome to check my solutions. They're posted on Teams. I just showed you some bare minimum stuff here, and so if you need more help, feel free to reach out and contact me. I'm so excited for our big reveal next class. Thank you for sticking with this course, and we will be back together shortly.